both our interest in dynamics, few body dynamics in optical lattices, I think that might be interesting for particularly for some of the nuclear theorists who may not have seen some of this physics before. It provides a novel way of looking at few body physics that I don't think has been fully appreciated or exploited yet. And then I'm also going to be talking about our perturbative calculations that we need for that physics. So, and this work involves a lot of collaboration with Ida and Dorta and Desmond, and also some postdocs back at NIST, so they can object or add as they will. The reason why this is funded by the US Army in part is that the dynamics that I'm going to discuss has behaviors that could lead to better scaling for certain kinds of phase estimation, so kind of quantum. So that's the aspect that they're interested in. All right. Also, I'm always getting questions about, where's American University, so I always feel compelled to. That's American University. And so it's about 5,000 students. It has a nice campus. This is in the middle of DC. So if I just pull back really quickly to orient you, here's the Capitol is here. Here's the White House. AU is northwest DC. If you go up further, you have NIST Gaithersburg. You go that direction, you have University of Maryland, JQI. So now if you go this area, you won't get lost. And if you pull back one more slide, you can see this is really great. So we're the center of physics, it turns out, in DC. Yeah, there's Georgetown and George Washington and Catholic are south of us. And NASA, Army Research Lab. I live close to NIST. So anyhow, so these are all, there's lots going on in the area. Although we're a small department, it's a nice location because I can easily get to lots of other people's places. All right, so outline. I'm going to start by talking about many body physics in optical lattices, and then I'm going to explain how that transitions to few body physics, which is really the interest that we have in this context, and then about effective interactions. So starting with the many body physics, I just a couple real quick slides for ways of making optical lattices. So counter-propagating beams in one direction. You can make standing waves that essentially slice a BEC into pancakes. And I just want to clarify right now that when I later talk about dimensionality, I'm working in 3D. I'm looking at, well, I'll also do calculations in 1D and true 1D and 2D. But for now, 3D, looking at confinement, so it's a quasi 2D in this case, but always in a limit where scattering lengths and other effective range or intrinsic ranges are much less than even the confinement direction in the z direction. So it's perturbative and not true 2D. Okay. Similarly, you can reflect laser beams up horizontally in two different directions and get the familiar picture of these tubes. Again, for us, I should have said quasi 1D, sorry. And again, scattering lengths will be less than the transverse directions. And then the final slide is also the 3D optical lattice, lasers in all three directions, and any slice you have atoms floating. And in this context, typically we assume that atoms are in the lowest band, although the physics we're going to talk about later on, higher band physics comes into an effective description. Okay. I also want to say a little bit about the states that we're thinking about, we're trying to calculate for. So in an optical lattice, a shallow optical lattice with a BEC loaded into it, if it's shallow enough, you'll have a superfluid. There'll be a well-defined phase from site to site. However, the number of atoms in each site is not determined because each atom's in a superposition over every lattice site. Typically, in the many body context, if higher bands are negligible, one describes the physics with the Bose-Hubbard model with a tunneling term and an on-site energy U, and just a two-body on-site energy is sort of the classic, right, Bose-Hubbard result. Of course, we know if this lattice becomes deep enough, there's a quantum phase transition at some ratio of tunneling to interaction strength. and you switch from a superfluid state to a Mott insulator state where now phase is essentially random from site to site, but there is a well-defined atom number on each site, in this case, 1 atom per site. So we have these two different interesting many-body states. And I want to say something about measurement, because that's all play into the few body, how we are able to probe few body physics. So if you take a superfluid and you suddenly release it from the lattice, let that cloud expand. After it's expanded quite a bit, after some time of flight, illuminate it, perhaps with absorption imaging. You will see, if this is a superfluid, where the atoms are all essentially in the k equals 0 quasi-momentum of this lattice, you'll see an interference pattern, and that will be your signature of being a superfluid. Just to show, these are beautiful pictures from Marcus Greiner's dissertation of releasing a superfluid, and this picture showing once it's released from the lattice, first of all, it's falling in gravity and it's expanding, and eventually, depending on when you image it, the size you get. And of course, you image from one direction, but you could image from various directions, and you get these beautiful, you would get in principle, interference patterns from all directions. If instead you have this Mott insulator state where the phase is effectively random from site to site, then you're not going to get an interference pattern. One way you can think of these interference patterns is like a multi-slit effect, right, where you have atoms that are being released from each site, but with phase coherence. If it's a Mott insulator, instead you just get an expanding blob, essentially like a classical blob that grows, like a classical gas. All right. Those are the traditional equilibrium states. What we have been looking a lot at are states that are generated by a quench. Now, there's a lot of discussion and a lot of papers about quenching, and so I want to clarify here, we're thinking about a quench in the opposite direction that people usually, most papers talk about quenches where you have, for example, maybe a Mott state, and then you make the lattice much smaller going to a superfluid state. We're going the opposite direction, starting with a superfluid state in a shallow lattice and quenching by suddenly making the lattice much deeper, turning up laser intensity. So that's any sudden change in parameters is a quench. And so what's one important thing about doing the quench this way is that by increasing the lattice quickly, the atoms don't have enough time to interact or tunnel. So that way we're not driving the Mott phase transition. Rather, we're essentially projecting this superfluid into this new, deeper lattice. That means, in a sense, the quantum field at each lattice site is frozen in place. The atoms are still in a superposition of all sites, so there's still well-defined phase at each site and not well-defined number at each site. If you did a slow raise, you would go to the Mott insulator. On the other hand, you do have to make this quench slow enough. You don't want to vibrationally excite atoms to the next higher band, because then that would just make things more complicated. So you can pick a nice time scale that drives you to a non-equilibrium state but doesn't excite to nice higher bands. And in that setting, the physics is still simple enough that you can really see and learn some interesting things. Is that?
So equilibrium means in the lowest block band, it's non-equilibrium.
Yes, in the lowest block band, it's non-equilibrium. Exactly. Okay. All right. So how does this turn into few body physics? Now I want to make this transition. That's the many body picture. It becomes few body physics because if you start with a superfluid where imagine the BECs being a single atom all in the same BEC wave function, tensor product at n times, if you do a fast loading, you can re-express that superfluid state as a product of coherent states at every site. So if there were no interactions at all, that would actually be exact. So you have this BEC, you raise up the lattice, and effectively at each site you can now think of a coherent state independently at each site. And in some sense, it's like you have an ensemble of coherent states at each site. They start out life at least with the same phase, so they actually still have phase coherence. They're not truly independent, but we can treat their dynamics independently. So, namely, each one of these states at a site is a superposition of different atom number states with the usual coherent state expansion. So it's a really interesting state if you think about it, because at any given site it's a superposition of being no atoms, one atom, two atoms, three atoms, and so on. If it's truly a coherent state, this expansion would keep on going. Of course, these numbers, these potentially probabilities defined, 1, 2, 3 atoms, become smaller and smaller. So this is an interesting state to create, because that means that in a single site we have a state that probes different few body physics, right? This state is only governed by a single particle Hamiltonian. This state is affected by a 2-particle Hamiltonian. This state, however, is sensitive to 3-particle interactions, if there are any, and so on, and 4 interactions. So you've made a kind of state that the different pieces of it are going to feel different Hamiltonians. Is that idea clear?
This is adiabatic rather than, so why do you say faster? Because this is left and right are the same.
Yeah, let me make sure the time scales are clear. So first, imagine this loading is fast enough so that you essentially you've projected this to this, and you haven't let the evolution start yet. All right, so this is what the state would look like at t equals 0, assuming that this is fast enough that we can pretend no time has yet gone by yet. Okay, so, and that's a pretty good approximation. Like I said, if you go too fast, you're going to excite to higher bands, so you have to make some approximation. But in the next slide, I'm going to talk about now the time evolution of the state. And the time evolution of the state is, well, this won't be a stationary state. So is this answering, or is this clarifying?
The left and the right are, in the large n limit, they are the same. You don't have to project. Or do you?
Well, if not with interactions. So interactions will give some squeezing. Although, in fact, with interactions, these will not be strictly coherent states. They'll be number squeezed. But to a good approximation, a lot of that can be incorporated simply by changing these parameters to reflect the number squeezing, so that if you look at the distribution of probabilities, they'll be different. But you can still treat it to a reasonable approximation as a product of distinct coherent states at each site. So this coherent state is an approximation that neglects interactions. But even with those, it's still, the main physics is still here. And we've done it in the number squeezing case, but I don't want to go into those details. I'm also just making sure I'm keeping track on time. Okay, good. Oops, here we are. Okay, so if you create this state and you ask what are the dynamics according to the Bose-Hubbard model in a deep lattice tunneling becomes negligible, so you simply have this two-body term, and these number states are eigenstates of this single mode Hamiltonian, this truncated Hamiltonian, with energies that are just given by the usual expression of half the two-body parameter, and n times n minus 1. That combination counts the number of pairs. So you can see the evolution, it looks like it'll be very, very simple, right? Of course, this doesn't do anything. If we set the single particle energies as our zero of energy, just to factor out that uninteresting piece, this doesn't do anything. Then we have this 2-atom piece, and it simply has a phase evolution given by the 2-body energy. The 3-atom piece, well, there's 3 different pairs of 2 atoms, right? 1, 2, and 3, so it's 3U2. Similarly, there's 6 pairs among 4 atoms. So if this Hamiltonian were exact, you would have still relatively simple phase evolution. These phases are going at different rates, but the important thing is that they're multiples. The energies are integer multiples of each other, so 3 times, 6 times. And what that means is that when you release your atoms, you can show that the visibility, if you're going to get an interference pattern or not, you can show that the visibility or the contrast of that interference pattern is directly related to the expectation value of the annihilation operator with this time-evolving state. And this state is simple enough that you can simply find the time evolution of the visibility in a closed form expression. And it's periodic in the time scale set by this two-body interaction. And so if you plot this particular function, what you get is the prediction that you have interference pattern, but then this is the hold time in the lattice. If you hold for a while in the lattice, these phases get out of sync, and when you release, you don't get any interference pattern, but it revives, and you get this collapse and revival. All right, so this is the standard collapse and revival picture, and I'm plotting one is units of h over u2, so the revivals occur at integer times in those units. All right, so this is what you'd expect if the Bose-Hubbard dynamics were correct. But I've already said, really what makes this more interesting, is that these different states shouldn't be governed by the same Hamiltonian. They should feel, in principle, 3-body, 4-body, yeah.
So after time evolved, the wave function on different sides don't talk to each other, or?
Yeah, for example, if you were to release the atoms at this in-between time, one way of thinking of it is that the states at individual sites now have randomized phases, and so when you release, they do not coherently, constructively or destructively add, so you just get a blob. It's also true that if you were to release at this moment in time, you can't unfactor the whole many-body. The many-body state is now entangled. It doesn't factor. Remember, at this initial time, it was essentially a product of states at each site, so it factored naturally. At these in-between times, it can't factor like that. So another way of thinking about it is actually the interactions are entangling the many-body state, and that entanglement destroys the interference pattern unless you wait for a revival when the entanglement goes away and it refactorizes again. So it depends whether you want to think about it as a single particle physics or as if there's little coherent states at each site that are somehow like matter waves.
But the state you write here, that's the state for the whole system?
This is per, I should put the, I dropped, sorry, I should put the site index. So this is per site. Yes.
Okay.
Yes.
And the initial condition, initial state is the inner product of all these states.
Yes.
And then after time, okay, it stays separable.
Well, I guess you're right. I'm saying that wrong. It stays separable. I don't know. What's the best way of thinking about it? Just the phases are randomized? Okay.
So phases are
Somehow that doesn't sound very satisfying, but maybe, what's that?
This is a many-body pure state.
Yeah.
There's only one random phase, which is the overall phase. So
Yes.
your pure state is a product pure state of each side.
Yes.
So their relative phases are totally fixed. It's only within individual measurements you don't perceive this phase. So this randomization usually means average over repeated measurements. This phase each time you collapse.
Well, there's a subtlety there because on the other hand, when you do a single measurement, you could do a single one-body measurement, but you have 100,000 atoms all at once. So in some sense, one picture is many measurements because of a one-body observable. So in that sense,
but it's a pure state. You see, you suddenly raise the lattice. All the phases, everything is fixed. I mean, it's just that you don't know, but it's a pure state.
I mean, I agree that the many-body state is a pure state, but the observable that gives the interference pattern is not stationary. So, right? I mean, it's a non-stationary state, and this expectation value has time dynamics. So that's still true, even though you're right in some global sense. There's a single many-body state. If this just shows essentially what you see experimentally, and these are the kinds of experiments, the collapse and revival experiments, going back to Bloch and Greiner, where they would see collapse and revivals, although notice that this decays away pretty quickly. They see revivals, maybe 4 or 5 revivals, and similar results a few years later at NIST. Well, what makes this very interesting, think about, let's go back and have another picture for what this state is doing. We have this superposition of different atoms And I like, nobody else likes to think about it like this, but I keep on trying to sell this idea. I like thinking about it as a kind of multi-body interaction interferometer, where you can think of the different components of the wave function as like different arms of an interferometer, each one experiencing a different Hamiltonian that generates a different energy. They're evolving effectively independently until released from the lattice. Then when they're released from the lattice, you're re-interfering those different arms, and you either at this end get a measurement that shows an interference pattern or not. So that's, in a kind of generalized sense, I'm thinking of this as a multi-arm interferometer that is detecting different M-body Hamiltonians, right? Each arm feels a different Hamiltonian. Otherwise, the same trapping frequency, everything else is the same. So the only thing that's different for each component state is whether it has a 3-body term, 4-body term, and so on.
But each arm is a different number of atoms. How could they interfere?
Right. So I understand that this is not a conventional. But this is the state. I mean, this is the state. I'm just suggesting thinking about it this way. I'm just suggesting that you can think about it this way. I'm not, that is the state. It evolves with these phases, and then when you release from the lattice, you compute the expectation value for the visibility, and we compute that, and that observable is highly sensitive to these energies, it turns out. So.
Can you tell me again how like that E2 and E3 they're not the
Yeah. So we saw if we just had pure Bose-Hubbard, this would be 1/2 U2. Or rather U2, right? Because this would be 3 U2. So they'd be related by integers. But if there's other terms in the Hamiltonian, these won't be. There could be extra terms here. That extra term will lead to a phase difference, and the evolution, the final observable, will be very sensitive to that phase difference. That's what makes this interesting, is that a small energy shift here beyond the expected 3 times U2 piece will actually show up as a phase difference that makes a big difference in the final observable. And that's another reason why I think this is a kind of interferometer, because usually that's what you want from interferometers, right? Small phase differences leading to a change in an observable. And this does just that. So I'll show you explicitly. So let's imagine that the true energy for still in the ground state had a 3-body contribution, that this would give the 3-body counting, and that this distinct from the 3 pairwise contributions. You had an additional parameter here. If you do that, then notice the evolution is going to be different. You have the U2 piece, you have the 3 U2 piece, and then you have this additional contribution. And if you now use this state to compute what the contrast of your interference pattern does, instead of getting collapse and revivals that always go perfectly like this, you find essentially a kind of beating effect due to this extra frequency. And in fact, these will go away very quickly. It turns out, for this particular example, this value is about 5% of U2, which turns out to be about the right value for the experiments. And notice, if we look back at the Greiner data, in fact, how their collapse and revival data.
What are the 2 curves in this picture?
I'll tell you in the other one. No, but remember, I'll come back to that. This is the Marcus Greiner data. When they saw this data, they thought inhomogeneities or some other effect was this causing damping. But actually, we had reasons to suspect that there could be multi-body influences, and quickly saw that even a small multi-body effect would cause a dephasing that was very rapid. But, and I'll still come to the other curve, if you go long enough, even with this extra frequency, you'll get essentially a kind of 3-body revival. This is a small energy, so its inverse is going to give a longer time. So you predict that if you can do these experiments long enough, you'll see a much richer kind of behavior of collapse and revivals. And this other fit is that You do still also expect some inhomogeneous damping. The lattices has some background harmonic component and things like that. And so when I made this, I also included some effect like that because I didn't know at the time how important that would be versus if there was all just 3-body. For these experiments, it's rubidium-87. I want to say, yeah, about 100 Bohr. And so U2, the frequency of the optical lattice was probably around 40 kilohertz, maybe 30 kilohertz. And I think U2 was about 2 or 3 kilohertz. And U3 was 5% of that, so about 150 hertz.
How do you compute U3?
I'll come to that. Yes, yes. So when we suspected that additional corrections could have a dramatic effect on these dynamics, and conversely, looking at these dynamics could be a tool for probing for these corrections, that brings us to our next stage of, okay, how do we calculate those from first principles? So that'll be the second part of what I talk about. Okay, and I'll show you, after we had made this plot, Bloch improved his experiment and came back to these experiments, and this is what they saw. Collapse and revivals that showed clear kind of beating effects coming and going. Obviously, there's other stuff going on as well. I mean, it's still a complicated system, and we do not understand every feature there. However, it is pretty clear that multi-body effects are in their collapse and revival dynamics.
But how would it look if U3 is 0?
If U3 was 0, if it was truly 0, you would just get it, yes, you would get that original prediction that was, am I too far? Here you go. This. Right.
But so this Bose-Hubbard model is still very simple, right?
Yes.
So when it comes, so couldn't you have 2-body corrections?
Exactly. Yes. So, and this is what the second you don't expect this to, but this was, even though this is what everybody was using, it's clear that that's throwing away lots of physics that would be relevant here. And so our goal was to figure out the most important next piece, essentially, and try to calculate it in a simple way. And okay, so that comes now to, that was our many body to few body. So we have this sense where you have these few body states, they have interesting dynamics, and their dynamics depend on their multi-body Hamiltonian that's governing them. And so now we want to calculate what those terms are, what those corrections are. So in some sense, you could also say this was the motivation for my talk. So we started by calculating effective interaction. So it turns out that these multi-body, 3-body, 4-body, are nothing more than effective interactions that are induced by the underlying 2-body interaction. But there's higher bands, there's higher orbitals, and excitations, virtual excitations of those higher orbitals generate effective lower body, lower energy physics. And so first we wanted to calculate for the isotropic harmonic trap. It turns out that's nice because you can do a lot of stuff exactly. Of course, harmonic oscillators are not, optical lattices are neither harmonic. They're approximately harmonic, but if you really think you're getting corrections from higher bands, then you think the anharmonic nature of the optical lattice is going to be important. That's something we're still calculating, actually, so I'm not going to say anything about the anharmonic corrections. Also, it turns out that even in the approximation that things are harmonic, they're usually not isotropic, they're anisotropic. So that I will talk about today. And it's interesting to think about their limits in terms of quasi-1D, quasi-2D. I put this here because I think Sheena said something. You mentioned, why not do 4D? So then I thought, okay, I'll put 4D up there. But I haven't calculated 4D yet. All right. So let's go back now to actually calculating what we expect should be a better improvement, an improvement to the Bose-Hubbard. So if we go back to the field theory, the Bose-Hubbard would come about from, at first order, I should say, would come about from simply an S wave delta function interaction. At higher orders, even this will generate, of course, corrections to the Bose-Hubbard, and those are important. We found that at the order we wanted to go, it actually became important to also include effective range corrections. And if you want to incorporate those in a local field theory, you can do those with the Laplacian of the delta function. It's sort of the next correction. So this Hamiltonian is sufficient, essentially is sufficient through third order if you want to get the physics right.
Is actually coordinate. Yes. You only have one field.
I only have one Hamiltonian.
One field.
Yes, and one field.
So you have one and two. That means coordinate. Yes. Do not mean two fields.
Oh, I'm sorry. Where?
One field.
The subscripts on the sides.
Oh, these are, well, those are, I probably should have just integrated out the delta function, and then this would all be the same position without. So that it didn't refer to different fields. It refers to two different places in space. Okay. But there is only one field. So, right, so we're dealing, and just bosons. Only, okay. But we can think of these two different interactions. I find it helpful when just trying to track the physics to try to do things diagrammatically. And so this delta function interaction will just be a normal vertex, and things that come about from this effective range interaction, I'll use a different vertex, a square. All right. So, okay, so here's the idea. We don't want a single mode, single band problem. We should do a multi-mode Hamiltonian. We could expand our field, for example, in harmonic oscillator single particle states, annihilation and creation operators for atoms in those modes. And if we substitute that in, it's easy enough just to get the general multi-mode Hamiltonian, right, with raising and lowering operators between modes, this being, the part generated by the delta function, this by the effective range. But it's hard to get a lot of insight, and we did not want to use this we didn't want to use this full multi-mode theory, because we also knew that to a good approximation, the original state was primarily in the ground band. And so this contains lots of information we don't want. And so effectively, we want to integrate out all of the higher modes to get an effective Hamiltonian. That's just a single mode for the ground mode, for a addressed ground mode. So that's what we've done. This summarizes basically that idea. Go, not good enough, too complicated, has all the physics, but we didn't want to have to do things numerically. We wanted to have a simple model, integrate out, and get back to an effective single orbital Bose-Hubbard, except where it now has not just the two-body term, but it has an effective three-body, effective four-body, and in principle, so on. And so that's our plan of attack, is to generate this effective Hamiltonian. And it seems to work pretty well, and it gives a very simple way. When you think that you still are mostly interested in ground band physics, it's a very nice way of getting a lot of that physics incorporating the higher band effects.
Are you actually integrating out those modes and determining these constants?
Yes. Yes.
So you do some kind of RG transformation?
Well, it's really, yes, it's equivalent to doing, yes. So
But
yeah.
here, what you have in mind is this particular mode A0 will be a Mott state.
it would really be, not Mott state, it would really be, if you like, the dressed or self-consistent single particle ground state in a site.
Yeah, but what you have in mind is...
Okay, yes, you could say it's like a Mott. It is like a Fox state in that single mode. So it's like a Mott, yes, exactly.
I would think if this were a superfluid state, maybe this would be a better approximation, because if it's a Mott state, we know that the particle Hall excitation is very important. I mean, so that means when you do the effective field theory, you kill all of those. Yeah.
Well, I mean, when we integrate out the higher modes, we are including a lot of that physics. So, right, I mean, we we integrate out the virtual states that have atoms excited to higher modes. So those are particle holes, if you like, in that language. So, yeah.
Ephemer-like states.
I'm sorry?
Ephemer-like states here.
What kind of state? Do you know?
So the answer is no.
Okay.
Because we are,
Right.
it's a choice, so we are basically, we are looking at
Oh, Efimov. Yes. Yeah. Yeah. Okay. Yes.
rubidium, and we are away from any Feshbach resonances, so the
Right.
atoms are interacting with.
I mean, in
For the
terms of
purposes of
Yes.
of these experiments,
Yes.
we don't see effects of that.
It would be nice to.
Correct.
Yes. I mean, certainly we would love to be able to do this and include that physics too. That would be a lot more challenging. But for our motivation, it's not in that regime for these collapse and revival.
The form of the potential is very important.
That's right. That's right. We're in a regime where this this delta function is a good approximation.
Partly with the context of these things.
Yeah.
We lack this superfluid state where we really think about at every lattice site that there is a superposition of atom numbers in the same vibration.
Yes.
But it's very hard to do that when the scattering length is large.
It was a bit confusing because in the initial Hamiltonian
Mhm.
you introduced only zero range interaction.
Well, and effective range.
That's what it was the origin of confusion.
Okay. Are you okay now?
So these few body calculations, they're basically an expansion around the non-interacting limit.
Yes.
Mm-hmm.
So that, so if you forget about the many body part, this is really an expansion around the non-interacting
Mhm.
limit
No.
and not around the epsilon
Yes, it's
limit.
clear, but I am asking about the solution of the initial Hamiltonian. Of course, for this Hamiltonian, I expect that you have to find Ephemer-like states. Well,
If the scattering length is large.
Yes. Right. Yeah. So from the big, we are totally in a regime where we do not have that physics.
Zero range
Okay.
model.
And maybe, I don't want to take the message ahead, but
Mhm.
we do see the need for three-body force at some order in the treatment, but not at the order that.
Right.
At this point, it's just
Yeah.
you're just doing what nuclear physicists are doing, right? So you do some
Right.
reduction of the basis space, and you just
Exactly. Yes. Right.
modify your Hamiltonian, but
Yes.
it's not a statement about what physics you're getting out at this point, right?
That's right. I mean, this is just a less fancy version of those nuclear physics calculations.
Oh, I wouldn't know.
Well, certainly with many fewer indices and internal states.
Right here.
Yeah.
It's killing me, the tension, how you're doing this now.
Okay. Well, it's a very straightforward. What we do is we simply do Rayleigh-Schrodinger perturbation theory at each order. Now, it has to be it's field theory, so it needs to be renormalized. So I should say we do renormalized Rayleigh-Schrodinger perturbation theory at each order and use the energy shifts at that order are then the parameters that go back into a single mode Hamiltonian. So so for example, first order, very easy calculation. Rayleigh-Schrodinger perturbation theory is just the expectation value of the interaction, and the raising and lowering operators, they naturally generate for you. You're counting n minus one term, and otherwise G2 and generates for you your two-body energy. So if you only calculated to first order, you could also say that this is basically in this context, the mean field result. It's just what people would start with the Bose-Hubbard.
But this works because it's essentially a recoupling problem. So if you have to do,
Yes.
So
Yes.
what people
Yes.
do in nuclear physics
Right.
now is it's called in-medium similar.
Yes, yes.
Renormalization.
Yes.
Then you would have to do something more like that.
Right, yes, we are very limited by needing to be essentially the scattering length over the harmonic oscillator length scale is our essential parameter here, and that's small.
So that this works.
Yeah, yeah.
Maybe for the nuclear physics people, another thing that might help is this is essentially the equivalent calculation bosons in a box with periodic boundary conditions that both Seilers and Sheena worked out. So it's basically the trap analog of that.
Yeah, the harmonic trap analog.
Yeah,
So
yeah,
don't
I
know.
just want to look, the tool is more interesting than the calculation is. I'm just, just that he does perturbation theory.
Okay, so let's go to second order. If we do second order, in Rayleigh-Schrodinger perturbation theory, it's this familiar expression, although there's some stuff hidden in it. But first of all, if I just had two atoms and I do this expression, I'm summing over intermediate modes, so that's summing over all the excited modes, not including the zero mode, where of course this would be singular, would be zero. And you immediately find, as expected, that this two-body shift in fact diverges. In this case, if you pick an energy cutoff, lambda, it diverges as the square root of the energy. So you have to do renormalization. We could draw this as a. These are not Feynman diagrams. They really are Rayleigh-Schrodinger perturbation theory diagrams, even though they look like Feynman diagrams in certain contexts. If you wanted to reproduce a formula at any order, you would come along. Each one of these vertices would be one of your overlap integrals between your four wave functions, your k's. And then anytime you get a cut like this is the energy denominators that show up here. Since there's only one intermediate time, there's one energy denominator here. And okay, so they're very similar. So we need to renormalize, and we renormalize in the standard way, which is that we have to accept the fact that our original parameter, G or U2, was really a bare parameter. And so you could think of it, you could either separate it into a physical parameter plus a counter term, and then have a self-consistency condition that determines the counter term such that the physical parameter really is a measurable observable at low energy. So that's actually usually how we do things, but it's equivalent here to rewriting that if I imagine, if I do to second order the divergent pieces here, and if I take the difference between the divergences and the divergences at a different energy scale, so in other words, you have you can imagine two different harmonic trapping frequencies, omega and omega naught. You can calculate this correction for those two different frequencies, and you will find that the difference between the corrections, the divergences, cancel, and what's left is a constant term, and the constant term and a function of these frequencies. That constant term is physically meaningful, and in fact, before I'm telling you what the result is, if you go to third order, you get more of these Rayleigh-Schrodinger perturbation theory diagrams. You get counter terms that are intermingled. Nonetheless, you can self-consistently solve for these counter terms at any order, plug back in, and get finite differences. And I don't want to. This would be better for discussion. So I don't want to go into the details of those calculations. But if you do this for the two-body, really, actually, very beautifully, what happens if you do it to third order, you can get an expansion of the two-body energy in terms of scattering length squared, scattering length cubed. You can keep on going, and these coefficients turn out to be exactly reproduce the Bush result if you were to take the Bush result and expand it perturbatively. So, of course, it's non-perturbative, but you could expand it around at low energy as an expansion in scattering length. And that's what these, actually forget these pieces, that's what these pieces are. These really funny terms exactly come out of Bush et al. Result. This has a little bit more because it actually also gives the dependence on these two frequencies. This is the frequency at which you imagine measuring the scattering length. And then this is the frequency at which you now want to make a prediction if you change the trap to a slightly different frequency. So these are akin to renormalization group kind of equations. They allow you to look at how the observable changes as scale, in this case, trap frequency changes.
What is your renormalization condition? Which parameter are you keeping constant? And if you say that in plain words.
maybe a different way of saying it is that if you were to calculate the second order, you would get that you'd get the first order result, you get this divergent result minus this other divergent result, and the renormalization condition says that let's call this thing the shift in the two-body energy, and it's a function of omega and omega naught. The renormalization condition is simply saying that when omega is equal to omega naught, this has to vanish. In other words, this has to be what you say it is. If you're saying that this is the physical two-body energy measured at omega naught, the perturbation theory has to be consistent with that claim, and the only way for that to occur is for all of this stuff to vanish. And so that's the condition. Then you just solve for the counter terms, you plug back in. And so it's rather, so this is not a new result, but what it is rather beautiful, I think, that it just, you would not, I don't know that we've ever had any insight like these crazy factors, but that's exactly what Bush-Adel would give if you expanded it.
So, sorry, what happened to the effective range?
For the, I left out the effective range contribution here. Sorry, yes. And at third order, we count the effective range because it involves two derivatives as effectively coming in at third order. So there's the effective range contribution at third order too, and I forgot to write it down. Yes. We have made, in this, we're making the assumption that the effective range parameter is roughly of order of the scattering length, and therefore, and that's why we're treating it as a third order contribution. Now, that's not fundamental, but we're assuming we're in a regime where that's true. So that's also limits the perturbation theory to that setting.
So if I would ask J squared over U, that means tunneling squared over the U you are calculating. If you write it in the same order, which order would it come?
Well, if there was significant tunneling, that would come in very important. Yeah.
The problem of an atom not to collapse in lots of ways, right? Immediately
Yeah.
it's a cosine-like potential, but we're making quenches from where this cosine is kind of weak to where the cosine is kind of
I
strong.
understand.
Yes.
Then that you can make a harmonic approximation, and that 2 leads to minima, but that the tunneling can be neglected
Yes.
after the quench, but not. So we're using actually the superfluid state just to make this what we call an interesting
Right.
initial state, which is the superposition of different
Right.
atom number and different side. But then we want to turn off all tunneling, and let's look at the evolution in a side. And now he's trying to derive the effective Hamiltonian for that problem under the assumption that we can approximate the cosine
Right.
by a harmonic one.
Yeah, this is a systematic expansion. So
Right.
J squared over U also fits with this parameter. I
That's-
just
that's
want to
the-
know
that's the-
which order it comes in.
Well, it depends on what you think the size of. It would come in already at first order if you think J is of comparable size to U. Yeah.
Correct.
Yes. So J should be there. Yes. If.
Limitations of the theory. There are lots of.
So think of this as just a valid. This is a deep lattice theory, or a perfect harmonic trap where there's no. But if it's going to be applied to a lattice, optical lattice, it has to be a very deep lattice, so that you can neglect the tunneling. Okay. Well, let's go back to. So this is all Bush-Adel, but what we wanted to really do is something that Bush-Adel didn't let us do, because remember, we wanted this three-body correction. That's the thing that we anticipate is going to really change the dynamics. And when you go back to this formula, this Rayleigh-Schrödinger second-order formula, it's only this result if you have two atoms. If you have more than two atoms, when you do the Wick's theorem, basically to expand this thing out, you get another term. And that term is equivalent to, well, it's an effective three-body term. You get another term involving three annihilation, three creation operators that essentially take three distinct atoms coming in, and physically it has a very simple interpretation. Two atoms interact. One of them stays in the ground state, one of them's excited for a while, and then it interacts with a third atom, and they both come back to the ground state. So this only occurs when there's three atoms. It gives a correction over and above the two-body Bush-Adel, and you can think of it as a simple diagram. And at this leading order, it's perfectly finite. So you've already done your renormalization for the two-body. This is just a finite calculation. And for the harmonic trap, you can calculate it actually has a nice closed form. It turns out that the energy shift, the three-body energy shift, is this parameter. It depends on the two-body energy that you measure. So you have to, again, you have to measure the two-body energy. You have to have that as input. But once you have that as input, you get this three-body energy shift. And this parameter beta just happens to have this result for a harmonic trap, for an isotropic harmonic trap. And this is, if we go back, this is the value when I showed you a plot of the collapse and revival falling off in just the right way. It's using this value and the two-body energy for those experiments.
It's not surprising that it's attractive, actually.
And I should point out it's an attractive three-body. Yes, so that's okay.
Why? Because second-order perturbation theory.
Both, right? Because both the two-body, the second order is a negative sign in front of it, so it's reducing the energy both in the three-body and the two-body correction. The two-body correction, of course, we did renormalization, so that had that complication.
People have analyzed, for example, the Bose-Hubbard-Knowles phase diagram, assuming a free-body interaction, but obviously they all use the positive U3 because of this system is
It's unstable.
Mm-hmm. But this is here, and of course the lesson for this is actually if you're going to use the Bose-Hubbard model for an optical lattice, this is here whether you like it or not. I mean, this is just the effective three-body correction, and so that physics is just always there. We also calculate this to third order because we did everything to third order also, both because that's the order effective range came in and also because our comparisons to Dorta's numerical simulations with her Gaussians, we found when we went to third order and we included the effective range, it agrees very well with those numerical simulations as well. So, whereas the second order is okay, but in some regions doesn't do well. So just for curiosity, if you do the whole third order, you get a longer expression. This is the third order three-body, so you get stuff like this that looks like loops, but it's finite. Stuff like this that is divergent, but the systematic renormalization puts in counter terms that will make it a finite difference. Again, it doesn't just cancel it, it leaves a finite piece, and the finite piece is physically meaningful, and all these other terms. So you can go.
You don't need a three-body counter term there.
At this order, we don't. At third order, we still don't need a three-body counter term. However, we're presently doing things to fourth and fifth order, and so I don't want to talk about that. Right? But then we do need.
Look
Yeah.
at the second diagram. So you
Yes.
say this triangle diagram is finite. Can I do this in the usual way with the three propagators, so that makes it more ultraviolet divergent? If you just have two, then it's
Yes. That kind of power counting works pretty well here for predicting when it's going to be divergent and not. And so, in general, when there's more in general, all of the divergences will involve loops like this or more complicated diagrams that have embedded loops like this in them. And doing the counter terms will always give you the right structure that will cancel even those cases. And anything like this, though at higher orders you can also get logarithmic divergences, which are another issue that I don't want to talk about right now. Yes?
I would presume that if you've got such a large effective range, you probably wouldn't even need a three-body parameter.
Well, and that's right. Right, and that's still also why I don't want to say too much because we're still trying to figure out precisely how relevant, when that physics.
Because the effective range would cut off.
Yeah, but this should go like dilute Fermi gas expansion, right? So, or also type expansion, so you would get it as a fourth order, you would get a 3x force. So that just has to do with the range of interaction, right?
Right, but I mean, but the effective range is such a large parameter that will cut it off before you get to that energy scale. It cuts off your U. Like it's like it's like having a Mary Fish fire, isn't it? Looking at the FMR effect. In that case, then it's dominated by the effective range.
So there is no FMR effect.
No, there's no SMF, but
Yeah.
but there will still be a 3x force, right, at some point.
But I guess cuts wouldn't be as relevant.
Yeah, there will be a three-body force. At the next order, they'll start to become a three-body force. Or yes, but its relevance in I can't tell you right now how it competes with the effective range in terms of relevance, but it is. But you do generate
Like what
these.
Hans referred to at some point. Like
I would claim this is all perturbation theory. So
Yes.
you're also going to treat the effective range in perturbation theory.
Yes.
And then this
Yes.
doesn't cut off anything.
Well, that's right too. That's true
It
too.
doesn't get the Efimov effect from this. Maybe
yeah.
we should leave that for
Yes.
discussion. And
Right. And I will tell you, of course, with the effective range, you now have the issue of it being a non-renormalizable term. So you also have to be a little bit more careful how you deal with that as well. So I'm going to use my last couple minutes to advertise some other results for discussion, just so you can decide if you want to ask me more about it. So this was the isotropic case. All this machinery works in the anisotropic case. You can do it anisotropic harmonic case. Although, as you can imagine, in general, if it's completely anisotropic harmonic, you can't do most of these sums analytically, and so you're reduced to numerics. But if you do cylindrically symmetric, I'm going to come back. This is the whole running of how these coupling constants change, but I just want to say what goes on in the anisotropic case. So if you do cylindrically symmetric, where you assume that here is isotropic, you can squeeze in one direction to get a pancake, the 2D or quasi 2D, another direction to get a cigar. We can get pretty nice results in this case and analyze what's going on. And so, for example, the three-body term still looks the same diagrammatically, but the sums are, of course, different in the anisotropic. There's these factors. You get a nice closed form result. It's still not a closed form. It has a sum, but this sum is so trivial to do that you can just plug it into Mathematica. And so you can easily explore what happens. This is the three-body term in the anisotropic case. And what's nice about it is that if you look at the three-body interaction, that's this black line. You can also go redo these calculations perturbatively for pure 1D and pure 2D. This blue line is pure 1D. This red line is the same calculation in pure 2D. And this black line is our 3D anisotropic case, going in the kind of the quasi 1D limit and the quasi 2D limit. And it's very satisfying that the 3D results, at least perturbatively, just map on to the perturbative 1D and 2D results at this order. And this is only at second order, so I also can't tell you if something crazy happens at higher order. But and of course the isotropic case, it agrees with our previous results for isotropic. Similarly, I'm going to skip. I can tell you about the energy, but I want to talk about the two-body. You can do the two-body anisotropic, and if you do that, you also get a more complicated expression, a coefficient for the two-body that has more complicated forms. And if you define this function f, we define this function f this way because, in fact, it's exactly the function that shows up in the anisotropic exact results by Idziasek. How do I say his name? I'm always saying Kalikar. How do I pronounce? Idzias. Okay, I'll have to work on that. It turns out, after the renormalization, just like we reproduce Bush-et-al, we actually reproduce their anisotropic results perturbatively. It gives you the exact same formulas if you take their formulas and you expand them out. So again, that's not new, but again, very satisfying that the two-body reproduces. But then what's new really is the three-body, where their results wouldn't have. There's just a two-body exact. So I can discuss more how that happens. The last two things I want to say is that if you actually do, I said I was comparing to exact 2D and exact 1D. Interesting things happen there as well. If you do the 1D result, the same methods, and expand that, they agree, oops, wrong spelling, they agree with Bush's 1D result. So in every dimension, things work. So Bush has the 1D dimensions. It also maps onto that nicely. The one thing I just realized yesterday, and maybe this should be expected, or I don't know, I don't understand the physics here yet, but it turns out when you do the second order result, for 2D, 2 atoms in this method, first of all, your divergence ends up being logarithmic in that case, and so you're kind of expecting that from other results. But then when you do the renormalization, it exactly cancels. There's no constant. You have a logarithmic divergence, and whereas in 3D, in 2D, you then have a constant, and then you have stuff that gets suppressed, that goes away. In 2D, there's no constant, and so after the renormalization, there's no correction at all. So it's as if the first order mean field term, at least to this order, is just exact, and it doesn't get quantum corrections. I haven't verified this to third order, and I would love to be able to resum, and somehow, because Dorota last night sent me the paper by Bean that has done this on a torus, right? That's right, I think a torus, periodic boundary conditions. Oh, I'm sorry. Silas. Yes. So I'm wondering if this somehow has a relationship to your result, which is non-perturbative, as I understand, right, to all orders. But
perturbative, but then.
Okay, but you resum somehow, right? So I haven't read that paper yet, but I was very surprised when I just did it at this order and it exactly vanished. And so then Dorota thought, well, maybe there's some kind of connection there. Maybe in a harmonic trap, the same physics is still occurring. So this is speculative, but it'd be interesting if anybody has insights. Okay, so I better stop, right? Because I think that's my time.
Well, we couldn't go on to 5 after, but we can also have more questions.
Oh, 5?
Well, 3 more minutes.
Oh, 3. Well, I'll 3 minutes of questions.
All right, so thanks a lot.
Okay, thank you.
Maybe you push the red button.
Oh, okay. Yes.